Hi, everyone. My name is Paul Bemis. I'm going to go ahead and get this webinar started. We've got about quite a few people online at this point. So I'm going to go ahead and start. I'm going to go over a few just details of this system we're using today. Go to Webinar. GoToWebinar has an interface over on the right-hand side of your screen. In there are the opportunity for you to ask questions. Please go ahead. If there's an opportunity for me to open your mic, if your mics are hooked up and you want to ask a question, I think we should experiment with that today and see if that works. Usually this is a one-way session where you type in your questions, which you can still do, but I think it's also an opportunity for back and forth. I hope to make this an interactive training session. It's more fun for me and more fun for you. The other point I'll make here is that we are recording today, so there will be a recording of this, and if any of you want my slides, you're certainly free to have them, although much of the 3D content will be contained within them and you won't be able to see the 3D. But there is a chat window, and I will be pasting some of the 3D into the chat window. We have a new feature in CoolSim I'll be talking to you about. So that lets us share 3D results. So let me go ahead and get started. For those of you who don't know us, most of you do. We've been around since 2008, so we're been around quite a while doing this kind of work. My background is mechanical engineering and electrical engineering. I worked in high performance computer design for many years for Hewlett-Packard before going into the software business with one of the partners I had at Ansys at the time. I also worked for Fluent and was responsible for all of their products as well. The CoolSim product is built on top of the Fluent Mesh Solve Post, so it is using the most popular and widely used CFD modeling software in the world underneath CoolSim. CoolSim effectively is an easy-to-use interface for building models and running models for data center. You people are busy, you don't have a lot of time, so we made essentially Fluent very easy to use by putting a front end on it that allows you to set up a data center and run it and get automated results. It's very cost effective. We try to get the cost out of it. It uses a SaaS model, software as a service, so all of the mesh, compute, and solve is all done on the cluster. Results are delivered right to your desktop. And we are experts in CFD airflow modeling. I've been doing it for about 100 years. So we have a lot of experience and can help you model just about anything. So let's talk about IT racks and how they work. IT racks, of course, are made up of servers. Each server has its own thermal management system. I want to point out to you all that what we're doing in CFD software is trying to set up and solve a steady state equation for something that's really not steady state. These servers have their own thermal management system. Their amount of air that they produce and blow is proportionate to sensors on it with a feedback control loop. The cooling unit is the same way. It has a feedback control loop. These units are not interconnected to one another and run on their own, so they often compete. The power consumption of a server is correlated to the speed of the airflow through it. It's proportional. Power consumption, by the way, of a server is also correlated to IT load more and more these days, so it is dynamic in that nature. And so the way that it works is this governing equation down here at the bottom is, of course, heat transfer Q is equal to mass flow rate times density times specific heat times delta T. This is the same equation that the crack uses. Okay, so they're all the same. In fact, there's been a lot of discussion about, libraries of equipment and so forth, of various kinds of equipment, but as long as you satisfy this equation and you have your geometry approximately right, you will be able to get good solutions from these kinds of tools. And we'll talk about the details of solution here in this session. But keep this one in mind. It's true for both the IT equipment and for the cooling equipment. And what's been happening with equipment, cooling in particular, of the IT servers is they've been getting better at it. So now they're able to use less airflow. This is a result of improved heat sinks, and I have an illustration of a heat sink here. The heat sink, its capability has an awful lot to do with surface area, as you can see here, but also its ability to conduct heat and pass heat through it and get it off that chip. So these things have gotten better. Also, the substrate is able to handle a little more temperature than it did before. And as a result, the delta T is going up and the flow rate has been going down. This is a chart right out of one of the ASHRAE manuals for TC 9.9. And you can see in the early days, we used to just overventilate. That costs money because, of course, the fan consumes quite a bit of power. It is cubic in nature in terms of its power consumption as a function of RPM. So there's been a drive to push these down by getting better heat transfer out of the package itself. And that has resulted in a decline of flow rate per kilowatt. I first want to apologize today for my English units. Most of the audience that's listening to this today, I believe, are in the United States. So I'm going to be using what I call American units, which include kilowatts for both cooling and heating, but CFM for flow rate and Fahrenheit for temperature. So that's my natural sort of set of units based on the US audience. So apologize for that in advance, my international customers. Now, in CoolSim, you have the opportunity to set up the rack delta T. You can model as an average watts per rack, or you can model as an individual server. In both cases, the user interface is the same. What will happen is, as you change the delta T, the CFM per kW will change. I just put in 1 kW here to the interface just to show you that at 35-degree delta T, you're dropping to 88. That's the lower end of it. This is a little aggressive if you ask me from a design point of view, because to assume all of your equipment is going to operate at a delta T of 35 assumes it's all brand new equipment. If the equipment's older in the data center, if it's an existing data center, I would use 25. In the old days, we would use 20. So a fairly good rule of thumb to keep in mind is 100 CFM per kW. You see here at 35, I'm 88. Over here, I'm 123. So you can take any data center, and this is again a CFM number, but you can take any data center, take the amount of load you're trying to dissipate, heat load you're trying to dissipate in the room, multiply it times 100 to come up with the flow rate you need to make that data center cool. Now, it says nothing about the ability to get the air, the cool air, to those servers. That's a CFD issue, distribution of air. But what it does do is give you a fairly good feel for understanding how much cooling capacity you need. Same thing on the cooling side. If you're trying to cool a 500 megawatt system, multiply it times 100 CFM, make sure you have at least that much cooling capacity coming out of the cooling units. You need to be able to do that in order to, of course, be able to cool it adequately. So it's true for both the servers and the cooling equipment. In the case of the cooling equipment, it's fairly easy, therefore, to size the CFM just from the amount of IT load in the room. And it comes out in the output. So here's a little bit of output showing you that. So in the top one, we assumed a 30-degree delta, and we're getting exit temperatures in the range of 90. So the inlet temperature is 60 and the outlet temperature is 90. So there's your 30-degree delta. This is after the model has been run. These are results. Down here, we're at 60 and we're at 95, average exit. Remember, these are averages. These are all 3D in nature. There's a contour there, so it's just an average. But nonetheless, that's how it shows up in the output. So let's take a look at some designs here. I'm going to take one design and I'm going to continue to talk about it and manipulate it throughout the talk today. This is a design I see a lot. I see this one being used quite a bit lately. A lot of the models that come in, a lot of the questions that come in evolve around something along these lines. This is a non-raised floor data center, not my favorite because it's very hard to modulate the air coming in and make sure everybody's happy. Remember, the benefit of a supply plenum is you get to modulate the air using perforated tiles. It is effectively a large duct that you get to basically adjust in any way you want. Here, you don't have that ability. All the air is coming from one side. Now, the way we're modeling this in this situation is these effectively are ducts. They're coming down from the roof. Oftentimes, there's a rooftop unit sitting up on top of this. It could have an enthalpy wheel in it. It could have big air handlers up there. But at the end of the day, you have to get air into this room, and it comes in through the form of inlet ducts. Now, we could have also just put these down here on the side and have it blow straight across. But I wanted to capture this dynamic right here, the dynamic of the air coming down, hitting the floor and bouncing, because it does have some effect on the cooling of the servers in the first part of this rack row. But this is often how I would recommend you model it. You do not need to model all of the crazy stuff up on the roof and have the unit there with all the parts in it. You can do that. But remember, you want to boil the model down to the simplest representation you can possibly make and still have it relevant to the question you're asking. The model should be as simple as possible, but not simpler. It should try to capture the physics that you're trying to capture, but does not need to be more complicated. Because these units are expected to be individual air handlers, you can turn them on and off in any kind of sequence you want and do N+1 studies. You've got a sealing return plenum. This design is hot aisle contained. There's no particular reason I chose hot aisle contained, other than I'm seeing a lot of it. I tend to prefer it because you've got buoyancy working in your favor. So the air coming out of the hot air coming out of the servers will rise. That's to your advantage compared to a cold aisle where it will want to hang on the floor and sit, and you have to push it up to get it into the inlets. Hot aisle is favorable from that point of view. It also makes the room cooler. One of the problems with cold aisle containment is the room becomes the hot aisle. It gets very, very hot. People don't like it. They go in and start turning down the thermostats, which make the air handlers work even harder and don't realize they're standing in the hot aisle. So we're going to be analyzing this one today. I have these models up in case you want to take a look at them. I will go to them periodically. Now in CoolSim, we have a pre-simulation report. This is always important. It's up here in the interface, pre-simulation. It allows you to take a look at what's going on in the room. Just a summary of the input data. So this room is 10,000 square feet, 11,000, something like that, 11,500. And the total amount of air coming out of the cooling units is 440,000 CFM. You can see right down here, the amount of air needed by the racks is 38810. And that's a sum, again, we're modeling here at average watts per rack. Early on in the design of a data center, you have no idea what's going in those racks. So average watts per rack works as well as anything because you don't know any better. We will show you later on how to dial that in tighter, but from the beginning, you don't really know what it is. And so you have to make some kind of assumptions. So we also model the containment as what we call a baffle. Baffle allows leakage. And this is where it's important to begin to use CFD modeling. You want to show leakage. Baffle is just porous media. It's something we've used in CFD for many years. It allows air to go through it as a function of pressure. You can think of it as a screen, an adjustable screen. It's just porous media. Now, the baffles in CoolSim are defaulted to 5%. Percent is a terrible parameter because, as I'll show you, it's is it percent of open area? Is it percent of delta P? Is it percent of total CFM? So, but we do allow you to set it because it's a common parameter. In this case, we're talking about 5% open area. So you can think of it as a screen with a certain amount of open area compared to closed area. And oftentimes the design community, the buyer, the customer, what have you, will say to you, oh, well, let's assume 10% leakage. I hear this a lot. The containment leaks at about 10%. And the question becomes 10% of what? Is it 10% of surface area? Is it 10% of total air supplied? This is not well defined by the design community. So for those of you who are designing or providing feedback to people who might be wanting to rent space in your co-location facility, drill on this a little bit. Try to find out what they mean by percentage because it's important. It ends up being an important component. So what you can do with baffles is you can adjust the leakage to match the expectation of where it will occur. So if they're expecting 10% of CFM, for example, you can just adjust the baffles until there's 10% of the air being supplied by the air handle is leaking through the baffles. You can do that, and we'll show you how to do that. But racks also typically leak within themselves. Oftentimes it's because a blanking panel is not being in place or rails leaking on the edges. And I'll take one apart for you in a moment and show you what it looks like inside. Most of you know what a rack looks like. And if you're a colo organization, oftentimes the installation of these racks and the maintenance of them is the responsibility of the customer, not you. Certainly not you, because you're probably way up front in the design community. Some of you are also operators, you're managing data centers, but you have little control over what goes on in that rack. And so, you know, you have to warn them that the key to successful data center design deployment for contained systems is leakage. The rails leak on the edges, the racks leak on the top, they leak on the bottom, and you can show them that fairly quickly. So we built here this design with the first design I'm going to show you with baffles for containment. Now the surface area here is the one that usually leaks. It's usually leaking on this side, and this up here allowing this section to leak is a conservative representation of what's going on down here. In this particular representation I'm using, these are tight together. These racks are tight together. They have a quantity and a size, and you just put them in. And then over here, I have not allowed, I flipped the switch so the end caps are not leaking, because they usually don't. Usually the end caps don't leak because they're solid, made of metal or whatever. You need to be careful about the bottom of them, making sure they're sealed to the floor. But it's important that there is some leakage. If there were no leakage, you wouldn't need to run CFD at all. I have had customers push me to do a perfect model with no leakage, but there's no reason to run CFD if there's no leakage. You can just assume it's going to be perfect, which it's not. So I'm going to pop a little video here because it's easier for me to do it this way than it is to try to speak and deliver this at the same time. But I'm going to show you quickly how to set these up. Here we've used the number of racks in a row. Okay, so that's one set you see on each side of this. And I'm using baffles here to set up the leakage. So I just dragged one in from the toolbar, and I'm here describing it as an end cap. And I put it in here and create its size to be appropriate. So I drag it over here and just set it up. You want it to overlap. You want it to be a little bit bigger than the rack itself. So I'm going to set this one at 5 feet so it hangs over on each side. And that's because we're going to slice right through the rack. The way the modeler works is that it's actually a mathematical function between inlet and outlet. So all the rack is a block with an inlet and outlet on it. It's not hollow. It doesn't have equipment in it. It's just a block. And we have written a user-defined function to handle the mathematics that I talked to you about earlier. So you can take these baffles and slice them right through the rack to build your containment. And it's really quite easy. So here I've made the first baffle, and then I've just Control-T, Control-C to get the second one in place. Now I usually take the first one again and just copy it. First I'm going to align them, so I just align them. Now I'm going to, oh, I see, I took a second one here, it doesn't matter. And then I'm going to change the orientation of this one so it's in that same plane. So I just changed the plane to be one more, YZ plane. And I want these to line up. Another thing about CFD is you have to have your edges and your objects lined up. We build a mesh, and the mesh is a very fine grid of three-dimensional objects. And it's important that it be done correctly. So you'll notice here I'm closing my gaps and aligning the fronts. This is a right mouse click option. It's very easy to do. You only have to do it once. They should look like a 45-degree angle, just like I've shown there. If there's a small gap in there, the mesher assumes that you're interested in that, and it will mesh the hell out of it and drive up the mesh count and drive up the solve time. So you want to make sure that it's lined up correctly. Here what I'm looking for is just a length. The length is a 66.1 from one of those baffles to the other. So now I just go back to here and I set this thing to 66.1. I use the endpoint instead of the size. That's kind of a nice feature. So I go to the endpoint and I just put 66.1 and boom, I have it down at the end. So now I have the left-hand side and I have to realign it because that geometry made a move for some reason. So I'm going to realign it. I'm also going to clone it. Clone is a very, very handy feature inside of CoolSim. It allows you to replicate with offset n times. So it's effectively a copy and paste, but it allows you to take an object or a group of objects, and that's where it gets interesting, and clone them, set offset, because there's always symmetry in the data center, or at least often symmetry in the data center, and you can take advantage of that by cloning. So here I'm just going to set this back up. I'm closing the gaps, aligning the fronts, and looks like I still have a little bit there. I want that edge to be very clean, so I close gaps. There we go. And over here too, I put my cursor over the one I want to hold constant, and the other one moves accordingly. So I just check it. Yep, it's good at the top, it's good at the bottom. Those look good. I've got the side rails leaking at 5%. So there's my containment. Now, as I mentioned, the reason I'm showing you this is that this clone feature is very fast. You notice this data center is very symmetrical. So I can take just the grills, just the baffles here, select them, and now I can clone it because the offset is constant. So I can lay out the containment for the rest of this entire set of data rows, rack rows, by doing one clone, because clone works for both objects and for assemblies. So this is an assembly. It happens to have 4 components to it. I'm going to offset them all by 18 feet, which is the on-center separation of my rack rows. I can also clone the entire rack row. So one of the ways to lay out this rack row is to build what we call a pod, which is one of these units over on the left, which consists of the racks and the baffles and the grills, and then just clone them all. And you see here I'm overlapping those returns, and that's important because you give the mesher a chance to put a surface on there, and they're slicing right through the racks. It doesn't matter. This model will run fine. So I wanted to show you quickly how to do that. It's extremely fast. So let me close this this particular image here, or this recording. I think we've seen enough of that. So now here are the results of this run, and I'm going to share these with you. One of the nice new features of CoolSim that's about to come out is the ability to share results. So here I've got the results hyperlinked in behind this image, and that's kind of a nice thing because you're then able to open them and review them, and in fact share them. So here I've opened up the entire set of output for CoolSim. Now this is in the form of an HTML doc. Okay, now one of the nice things, as I mentioned, is I can share this with you. So in your little chat box that you have, I am able to Control V in my data center report. So all of you in the audience can now go to your little chat box and hit that hyperlink and open the same exact report I have. That's pretty nice. I've never seen that done by anybody before, except us. I've wanted to do this for years while I was at Fluent and Ansys, but we didn't have the technology to do it. Now we do. So this output report consists of a bunch of stuff. Here in the white are all of the details. So let's first take a look at the data center description. It lists the size of your data center, the depth of it, and so forth, and the size of it. How much is removed by the crack unit, what the number of rows, the amount of flow through a rack, the number of crack units, how much. So I'm blowing 480 here, and I only need 411. This is an N+1 design. They're all right now fully on, they're fully cranked, and this is how it behaves with them all on. Now I can go down here and take a look at the crack performance data and see that I'm blowing air at 70 degrees. Generally, people want to do this at higher temperature. Remember, you're standing in the cold aisle in a hot aisle design. So You want to get the supply temp up as high as you can because that's where you get your energy savings. If you have any kind of free cooling going on, or air side economizer or water side economizer, if you have pumps, compressors that are being used, you want that supply temp to be as high as you can because that's going to give you the most energy savings. Likewise, you want your return temps to be as high as you can because that gives you good efficiency on the heat exchangers. Higher the delta T, the better. So this is all good. Now over here on the left are all of our 3D slides. This is all of the 3D material you can see if you're looking at this yourself. Let's first take a look at path lines from racks and PDUs. Way down at the bottom, lower left-hand side, you can pop this window. I want you to take a look at this. In fact, one of the nice things about this new system is I can even take this and put this in the chat box. So I can take this individual image and put it in. So now in your chat box, you're going to be staring at the same image I am in case you had trouble finding it. Now, this is Ansys technology. This is nothing we created, but we get to take advantage of it because we're their partner. And you can see here the hot air coming out of those units at somewhat 93 degrees roughly. There's a couple things about this I want to point out. Hot aisle contained, a very common structure here. Let me go to Z. I hit my Z key. You can rotate these around with your X, Y, Z keys. You can turn off perspective with your N key. Up here in the upper left-hand corner, there's a little feature that allows you to shut off the rear of the room, was what I usually shut off. And in this case, let me also shut off the baffle surface so we can see in there. Let me shut off blocks as well. So there's a nice clean image of just exactly what I want to show you. So have a look. Here's what we have going on is air coming out of these servers very, very fast. It's hot. Remember, they're blowing this pretty hard to each other. Now, we remember from our friend Bernoulli, right, that total pressure is the sum of static pressure plus dynamic pressure. As this air comes out and it slows down because they bump into each other, they hit each other. As they hit each other, the velocity drops, static pressure rises. You have pressure built up in your return. Now, most people will, from a design point of view, say, oh, no, it's a positive pressure environment. Remember, I'm blowing more than I need. So I have more air entering the data center in general than the racks require. Therefore, it should be a positive pressure. However, pressure is not uniform, particularly in air. It's not uniform. It will vary. So you've got this dynamic going on here where these racks are blowing into one another, and you can see it in the pressure plots. So let's go to pressure at 3 feet. It's a little harder to see it in pressure plots because the pressure plot generally gets obfuscated by things like the cooling units. But you can see there in general, it looks fairly good. You want this pressure in here to be lower in general. But look what's going on in between those racks. You can see it starting to seep in. You can see some of that pressure starting to push its way in and out. You can see the pressure starting to manifest itself in here. You can also see it in temperature as well. So let's take a look at temperature. Go up here to temperature, and we can take a look here at Y slice. So here's a temperature plot, same thing. You'll see it a little easier. So here's a top view of that temperature. Okay, and you can see it starting to leak in between those servers right there, and temperature getting in there. Not too bad right there, but as you go closer to the top, it gets worse. So there are some results. You can do that for these data centers. This is a 60 degree supply air temp was the first one I did. I did another one at 70 degrees. Now, let's take a look at this set of results at 70 degrees. The name of the program I am using is CoolSim. There was a question that came in about this program, CoolSim. And the next thing I wanted to do here, let me make sure I've got the right model. You can see the model right up here. So let's take a look. Yeah, this is the model that I'm interested in seeing. So here's a layout of the model. Again, the rack rows are listed there, and then you have containment around them. All right, so one of the things in CFD, under the normal conditions, they should operate. The question becomes, what happens when you have a cooling unit fail? So here I've set up 4 runs at once. In CoolSim, you can set up 4 concurrent runs to take place, and you can vary the parameters. So here what I've done, I've shut off crack 0, and then crack 1, and then crack 2, etc. I'm going around the room shutting these things off. This one's running at 60,000. When I shut them off, I need to turn them up, so I've got them set at 60,000. I've got the supply temperature set here at 60 degrees Fahrenheit. You can adjust the flow rate and the supply temp in the on-off state in this. So let's go to run 0. In run 0, as you can see, I've got crack 0 off. So let's go there and take a look first at the air coming out of the units to make sure that they're set up correctly. So here is unit 0. Could be any one of the units. You see it's off right there, and I'm pushing air down this room, and you see the path lines of air coming out. Again, I can share this with you if you want. You can keep clicking on these if you want. It's up to you. So I just put another one in the chat box. You can see this one. Now, what this is going to do is cause a non-uniformity of supply. These other units are going to have to work harder to supply cooling for these units. The most important thing to look at is the rack inlet temps. Are they meeting condition? Rack inlet temp here is this plot called ASHRAE recommended range, and it allows you to see whether or not it's in range. So you see green means it's in range. If you're below 64, it means it's out. This is often called a go, no-go gauge kind of thing. If you ever took machine shop, you'd come up with a go, no-go gauge, which meant you're in spec or out of spec. And you can see these are out of spec on the low side. If there was any red, it would mean they'd be out of spec on the high side. So they're in spec down at this end, but what it's showing you here is non-uniformity in the direction of the rack rows. And the reason that's true is because near the racks, near the supply, you have a high amount of velocity. And over here, you have a high amount of pressure. As the velocity trades off. So here I have high velocity on this side, but low pressure. Over here, I have high pressure and low velocity. And what's happening is the air is being used up by these servers near the end, these racks near the end, and not making it all the way down the row. You can see that in a couple of other areas as well. The temperature will tell you the same thing. Here's a slice of temperature. We're just slicing right down the data center here. Let me rotate this around so you can see it. And I'll turn off perspective so you can look straight down at it. We're looking down at a height here of 6 feet onto the data center, and you see that the temperature is really not uniform in here. Remember, we've got a unit out over in this section, and you see leaking occurring here, you see leaking occurring here, you see quite a bit of temperature leaking into the cold aisle. You can see it leaking out the end cap here and coming around the corner. Leakage. Leakage is your enemy when you're doing containment, and you can model it many different ways. I also wanted to show you here, one of the other slots is supply velocity. So from cracks, here is one of the issues I wanted to show you is the bounce. This is kind of an interesting shot I was looking at earlier. Let's take a side shot here. I'll rotate this around. And then open up, whoops, a little too far. And then what I'll do, again, with this nice little viewer that Ansys has that comes with your CoolSim software, you can turn off blocks so you can see what's going on. I'll also turn off the rear of the room so you can get a cleaner shot. There you have it right there. So let's take a look at what's going on. So you have air coming down here and doing a bounce. It's bouncing in the back and it's making a circle over there. It's also coming down here and bouncing off the floor and then bouncing back up. So you're going to have a difference of cooling across the height of that rack row due to the behavior of the air in the room. You can see it right there. See that air bouncing off the floor and coming up. One of the things to be careful of in these kind of designs is velocity profiles at this end of the rack. These are pretty close to these cooling units. And as a result, this velocity will be high. High velocity again means low pressure. So there's going to be, as I mentioned, the pressure's building in here, even though we're supplying more air to the room than it needs, to the full racks than it needs. The local effects will have importance. Here we have a high velocity moving down the center. If I look at this at a velocity map, that will be high. Here I'm having a fairly high pressure caused by, so there'll be low pressure there. High pressure here because the exhaust plumes are banging into each other, causing the static pressure to rise, and it'll begin to push back through those servers. So leakage in these servers is extremely important, and protecting them with proper blocking and so forth, kind of the devil's in the details kind of thing. All right, so now here's the same model at 70 degrees. Whoops, did I not? Yeah, I guess I don't have that hyperlinked. At 70 degrees, the whole thing just simply gets worse. Let me see if I have it at 70 degrees. I have a number of different models here running. So let's see. I can't get to it quickly. There we go. There it is. Yeah, the report's probably not done yet because I was running it just before. Oh, it's downloading. So we'll just let that aside for a moment because that'll be up in just a second. And let me keep going. Okay. All right. So modeling IT rack leakage is quite important. I mentioned the first one. You can model it with just straight baffles surrounding the rack rows. The second thing you can do is put a gap between the racks. Again, we're modeling average watts per rack here. Don't need to do that, but that's a fair way to do it. You can get more detailed. I'll show you that in a moment. And here we've let the baffle leak right down at the rack level, and I'm using blocks above it. So that's one more level of detail that you can do. It's still pretty quick. You lay out one rack with a gap between them, you clone the rest of them. Once you have one set done, you clone the other set. Once you have two sets done, you clone that set. You can lay out a data center extremely quickly in CoolSim using that method. And there's a little video here. I'm running out of time, but this little video shows you how to do that. I basically just described it. It's much like the first one, except now we're putting explicit gaps in between the servers in that room. You can also go one more level of detail. Here we're getting into the rack itself and we're setting the specific amount of load in a rack. The earlier model I used assumed average watts per rack. So the heat load was uniformly dissipated across the rack. That's not usually the case. Usually it comes in lumps and it's kind of chunky. So here in green, you see the servers themselves being defined. So here I'll have a uniform load of certain amounts. So in CoolSim, you have a rack builder tool. It pops up a spreadsheet like this. So this is the one for one of the rack rows. You see we're defining the server in here to be a certain number of U's. Each one of these lines is a U. So you can say I took 4 U's here or 3 U's and create a delta T for that individual and a flow rate for that individual server. So here's what there's also one more level of detail you can get into where you can put the rack rails in. So I'm going to pop over here to that model to show you. This is what that model looks like. And here, I've got a couple of them here. Let me make sure I've got the right one. There's the original one. You notice I can also run multiple copies of CoolSim, and so can't you. So here's what a detailed server looks like. I wanted to take one of these apart for you and kind of show you. This one has a chimneys on the top of it. So this is a chimneyed rack. I'm going to show you these results in a moment. But here we've put everything in it. So let me just take one of these and ungroup it. This is an assembly. I'm going to ungroup it here and show you how this is built. So let's first take the side panel off. And you'll see that here we have gone into the rack. Now the rack in this case is only about 19 inches wide. That's what equipment usually is. And it's sitting inside a box I made. And it has a passive chimney sitting on the top of it with a diffuser inlet and a diffuser outlet on it. So the air will, just like in the real world, go from front to back. So the air is going to pass in the direction of that arrow. Now, this is the culprit right here. This is rack rail leakage. And you want to set this for a certain parameter to allow this kind of modeling to occur. This one's at 5%. We also have put the front on this particular device. So this is the front grille. We've modeled that as well. But you can see you can get into as much level of detail as you want to. And you can set all these rack rails to leak. You could even take one rack rail and put it across the whole row, because all I did is take the first group and clone it. But the air will come out of the back of this and supposedly just go up through the chimney. But it doesn't always work that way. So here is some output for that particular model. And I want to show you what's happening. So let's go to the racks and PDUs right here. Let's take a look at this model. I'll pass this one over. Oh, I can't because it's inside the modeler. I'll have it in a moment. I can share with you. But let's take a look at this one. And let's see what's going on inside that rack. So we can again go here and we can turn off the block. This is pure output. I'm just using this as an output here. Now look what's going on there. So the air is coming out. Again, it's coming out at high velocity because there's a server there dumping heat with a fan on it. It's bouncing off that back wall and it's creating pressure, right? Because we went from high velocity to no velocity. So any dynamic pressure got transferred immediately into static, and it's pushing. And guess where it's pushing? It's pushing on the front of that, pushing out the front. And this is just a normal chimney sitting on top. These are what we call passive chimneys. Same idea with hot oil contained, same exact issue. It comes out, it bangs into something, often the other server. If they're wide enough, you're good, but sometimes they're too narrow, and it wants to leak around and come out the front. And you say, well, you know, you've set it up incorrectly because there's no ceiling plenum there. But my point is ceiling plenums are notoriously leaky. Most ceilings in a data center are made of a standard drop ceiling kind of structure, much like we have in the basement of our homes. So they leak. And that leakage creates a situation where there's no low pressure to pull it, and you're really forcing it up by the server. And buoyancy. Buoyancy will help you. But you're pushing air up, you're having to change its direction. This causes issues. So if we look at pressure here, at let's say 6 feet, which is a good place to look. Most of it's all the same. Pressure is a little tough because of the room. It's all the same, but I did clamp it. You are able to clamp in CoolSim, and I clamped this before. And let's take a look at that pressure profile, and you can see at 6 feet what's going on there. It's pushing. It's pushing to the front. So these racks are leaking around the rails right there, and that's exactly where they leak. They leak on the rails, they leak at the top, they leak at the bottom. And if you don't include some kind of leakage in your model, you're not going to capture the issues associated with a specific data center. Which again, back to the macro problem is we're supplying air from one side. So the pressure variation across that room is going to be non-uniform. It's going to be high at the far end when there's not a lot of static pressure, and it's going to be low near the beginning where there's a lot of dynamic pressure, a lot of dynamic velocity. So that's how they work. And you can see this in the thermal plot as well. And I did not put a ceiling plenum here to emphasize this point because it's not unusual for these ceilings to leak so badly that you really have no pressure left, no negative, no low pressure left to pull the air, particularly in a case where you're trying to pull it all the way across the room because the air handler near the rack you're most interested in is in fact down. Here's leakage. This is temperature now we're looking at. Temperature is pushing out and it's beginning to affect those racks. If we look at inlet temperature for that particular design, we'll probably find that it's failing. So let's take a look at that one. Shows up on my other display. I have to drag it over here. But here's inlet temp. Oops. You see it's not uniform. It is passing in this case, but my supply air temperature is probably low enough to allow that to occur. And if you run your supply air temp up, this one's going to fall out of spec It's also falling out of spec on the edges here. Now you may say, well, that's not a big deal. I can get away with that. Well, that's maybe true. Maybe true, you're fine. But the CFD is showing you that they've got issues. And you see I'm supplying air at 60 degrees. It's pretty cold. You really want it to be more like 70 on the supply. So you can use structures like this and create more detailed racks if you want. This is an example of that. These racks in this particular model have blocks all the way around them. They have leaking rails. This is a block. I have these details here as well, so we can take a look at these. One of the ones that's interesting, and I can share these with you if you like. This one is on the output. So Control V, if you look in your chat box, you can get at this one. So here, let's take a look at temperature. I'm sure we're going to see a similar thing. I don't know what my supplier temp here is. I'll have to take a look. But we're going to see a very similar thing that we saw before in the model I just showed you. If we say this is a contour plane at y equals 6 feet, you see non-uniform temperature. If I take off perspective by using the N key, you can see exactly what's going on there. Temperature's leaking out those rails, coming out and infiltrating the front of that server. And what's interesting to note is where is it happening? These are the crack units. These are the ducts bringing the air handlers down and dumping them in the room. But remember, we have quite a bit of velocity coming right out of here. That creates a bit of a low pressure in this region. So look where it's leaking. It's leaking near the low pressure. So the low pressure caused by the high velocity in the front of these servers compared to the higher pressure here, because the air flows are banging into each other and the velocities are going to zero and the pressures are going up, is causing leakage through the rack rails. Now, to prevent that, you've got to take a lot of attention. You've got to pay attention to rack rails. You've got to seal them, particularly under the racks is important. This one often gets overlooked where you're down below the rack on the floor. People don't pay much attention to what's going on down at the floor. Under these racks can be problematic and cause issues. Let me see what we have for supply air temp. 70 degrees is our supply air temp. Let's go have a look at our rack inlets. And if we look at our rack inlets, they're still in pretty good shape. This is probably not an N+1 design. It's probably just the base design. Yep, they're all running. Look, all the cooling units are on. Okay, so they're all delivering at 70. Now the problem is you lose one of those and that non-uniformity you're seeing becomes an issue depending upon which one you lose. And this is why it's important to do an N+1 study of all the possible failure modes so you know which ones are the worst. Here's temperature again. We're looking at temperature. This is a Y component. And we're looking and we see temperature, high temperature on the far side. Why? Because the air is being absorbed into the racks over here, heat's coming out and polluting the airstream. This is a pressure plot. So we're seeing high pressure on the far side, low pressure near the racks, near the cooling units where the velocities are high. So this is pressure, not temperature. And probably you can see a variation. Yeah, I'm up too high to see the variation between the racks. So this one's a more detailed model. Answers are effectively the same. That is to say, we've got an issue in this design with leakage that's going to occur. Our jobs as advisors is to make people aware there's leakage, ensure that they're putting good material around the perimeter of the rack. There's no gaps between the rack. Underneath the rack is very important. Okay. So I'd like to open it up for questions. I do see we do have some questions here. I wanted to leave enough time. It's about 10 minutes of. Let me just go through some of the questions here. Can the detail be reduced to an individual unit to show the difference between switches that vent front to back, create stack temperatures? Yeah, switches are old. They vent to the sides there. Yes. Yes, you can do that, Michael. All you do is build a stack with components upon each other that blow in the other direction. Not hard to do, takes a little time. The modeler itself allows you to adjust the position of the rack any way you want. So you effectively make a stack that looks like this one, and you just have airflow pointing in different directions, and you stack them on top of one another and then make a group out of it and save the group. By the way, you can save any of these groups in CoolSim. So if you build something you like as an assembly and you want to save it, you can save it in your local library system. You can also export it and write it out to a file and save it as a file. They're not very big. So here's a group. This is one of these rack row groups that I've built. I can export that as a CSO file if I want to, and it's quite small. Okay. Can CoolSim account for non-uniform sealing materials? In some data centers, the plenum may be removed because it's fire retardant. Yes, you can. In fact, one of the runs I made, leaking ceiling, I just finished it. So here's a leaky ceiling. You can model a leaky ceiling by just, in this case, all I did is simply put more grills in it. Here I put a grill along this edge over here because I figured that's where it would leak. Set the leakage at a certain percentage. So remember, in the hot aisle, you've got these grills anyway. You can also randomly put other grills with lower percent area open on them to model the behavior. But it is an assumption. Again, what we're doing in CFD modeling is we're making assumptions. We have to, because there's no real data on much of this. There's no real data on how leaky is a rack. There's no real data on, there's not even real data on servers. We don't know a lot about the servers. My job early in my life was build thermal control systems for servers. They're all a little different. They behave a little different, and the manufacturers aren't particularly excited about sharing that information with us. But you notice here at 70 degrees Fahrenheit, let's take a look at run 0 with one of these units off. And let's just take a look at rack inlet conditions just to see how this ended up, and that's not a surprise. So we've got problems over here in this section of the data center with a leaky ceiling. And it's very evident why. Again, this is N+1 job, and let's see which one of these is out. We can tell down here a couple different places, but supply path lines from cooling units is where you can tell. And so we can tell by looking from here that this unit right here is out. So when this unit's out, these racks are going to starve, particularly if there's leakage in the ceiling. So a lot of people will simply do the algebra and they'll say, oh, there's plenty of air in the room, we're all set to go. Not so much. If you lose one of these others, like this one, has to supply air over to satisfy the needs of this rack. To do that, it's got to get the air over there. It's lots of blockage in the way. And furthermore, it needs to pull the hot air all the way back across that room. And if the ceiling is leaking, then you lose that pressure gradient to pull it. And it just goes up and fills the ceiling. We can probably see it in the return path lines. And it pops up on my other screen. So here it is. Lots of air in the ceiling plenum, and it has nowhere to go. It's causing all kinds of problems. You see it leaking out over here. This is one of the models that I was looking at that is uniform in its rack structure, but you see it's leaking out of the containment and has nowhere to go. So we've lost the pressure gradient. I don't know if I have a pressure gradient up in the ceiling. I probably don't, but you can put one up there. I have a pressure at 7, probably not high enough, but we could change that. So you need to model leakage. You can model in a variety of different ways. You can let it leak around the rack itself. You can just let it leak through the containment, do a fairly straightforward representation like I showed you before. Those are really fast. Remember that as you increase the detail, the level of detail, the amount of time, both in terms of development of the model and the runtime, will rise, because the runtime of the model is correlated to the level of detail you have in the room. The mesher builds a mesh, and the mesh is correlated to the smallest objects in the room. So if you've got a 1-inch gap in the model, it's going to show as so let's take a look at our mesh here. I'll show you that. The mesh is shown here under meshed. And this is a mesh of a fairly, the more simple one that I did. And you can see the cells there, the cell count. this is what we call a surface mesh. And the only reason we don't do the volume mesh is you wouldn't be able to see anything because it would be completely full of cells. So I'm showing you just what the cells are on the surfaces of the objects in the room. For each one of those cells, we do differential equations, conservation of mass, momentum, and energy for every one of these, and interpolate the results across the room from the origin. That's essentially how it works. As the models become more detailed, that mesh goes up. So here's a model with quite a bit of detail in it. I don't know why it doesn't have any results though. So let's go here. I'll show you one that does have that amount of detail in it. We'll take a look at the mesh on that one. Let me just pop over here and make sure it's the right one. So here's a model. And this one has got more detail. You notice in this one, we've put in the rack detail. We've got the servers modeled in them. The other question when you go for detailed model server is, what is the load distribution in the vertical direction? There's no way really for you to know what that's going to be. So here I picked a pattern, a random pattern, and then just replicated it. It won't be the case in the real world. There won't be that much symmetry, but there's no way for you to know that in advance. So you have to make some assumptions. But let's take a look at the output on this one. The size of the mesh is reported right here. So that's 5 million cells. It took 6 cores. CoolSim runs on multi-core. So it took 6 cores to run that. Probably ran for about an hour to get that result. Let's take a look. You'll notice the mesh here is much more dense than it was before. Can CoolSim account for non-uniform sealing materials? Yeah, well, it's a leakage issue. So here's the cell count. This is what the mesh looks like for this particular design. You'll notice the cell count's higher because we've got to get right in there and measure the model of the rail, the rack rail itself, which is a little hard to see, but effectively is inside there. So this one will run a little longer, it give you more granular results. So the output on this one looks, if we take a look at temperature, I think I've already shown you. Can the detail be reduced to an individual unit to show the differences between switches? I already handled that. So if any of you have any questions or you'd like to ask a question, I see someone has a hand up. Maybe I can open a mic here. If any of you would like to ask questions, feel free to open the mic up here. I'll open it for you. If you put your hand up, you can ask a question. We talked about, there's a question about energy savings. You can model energy savings in this as well. Non-uniform height. Yep. So here's temperature again. We've got leaking racks. I showed this to you earlier, I think. So there's the leakage caused by the high velocities. I guess in summary, one of the other things I would say to you is that as analysis people, we get asked oftentimes to tell the customer that everything's going to be fine. And in designs like this, it's not going to be fine. There's going to be issues associated particularly with the non-uniform distribution of air in this room. Leakage is the culprit. They'll often encourage you to not add any leakage or reduce leakage. There'll be no leakage. And it is our job, I think, to remind them with images like this that there will be leakage, and leakage will cause the performance of the data center to degrade. You'll end up with hotspots, particularly in N+1 cases where you've got one of the air handlers off. And it's important to model so that you can show them. One of the great things about CFD modeling, it allows you to see the air. It's really one of the only ways that you can illustrate through high fidelity color just exactly what you're talking about. And taking some output like this and sharing it with them, as I've done with you through something as simple as chat, or you can send it to them as a hyperlink and they can look at it on their phone, or you can bury it behind an image and save it as a PDF and hand them a PDF, and they'll be able to open the images in full 3D and be able to see them. So the technology has come along to the point where you can now easily share it. You don't have to have special viewers anymore. You don't have to have special computers. This is important, and I encourage you to use it. If you don't have it, let us know. We'll get you a copy to experiment with. That's not a problem. We provide this. And if you in the audience, those of you have ideas about other topics you would like me to review in one of these sessions, please let me know, because there's a lot that I went over in just 45 minutes and was not able to give it the level of detail that you may like. But we can talk about control systems, we can talk about variable speed drives, we can talk about energy efficiency, energy consumption, we can talk about modeling various cooling units or modeling various cooling designs, evaporative cooling. Whatever you want to do, I will continue to try to make these sessions educational. Use this tool as a way to illustrate how you might want to make your case to whoever it is you're working for or working with. This tool is extremely effective. It's quick. It gives you the results you need. The output reports are fully automated. These reports that I'm showing you are coming straight out of the system. I did not have to create these by hand. They're fully automated. It comes with a full set of 3D capability as well that can be used, and it can be shared. So a question came in for CFD simulation. It should be in the design. You are right. It should be in the design, but it's not always. For those who, see, we've got some problems going on up here. For those of you who are in the design community and you're not using CFD, I'd encourage you to use it. Get a copy of it from us if you want to evaluate it. We do allow evaluations. We have 30-day evaluations if you want to experiment with it, to show it to your customer or your boss or the people that you're working with. We'll help you set up some runs and show the value of it. We think it's an important decision support tool. I also want to point out that it is not a forensic tool. In other words, this kind of modeler in general, CFD, is not going to give you the same exact temperature T that you go measure in that data center. Modeling and measurement are two different things. They are highly correlated, but they're often hard to replicate because of the assumptions made in the case of modeling. You have to make some assumptions. As I started the presentation off, I told you that a data center is not a steady state environment. It's a transient environment. It's changing all the time. When cooling units come on and off, when loads hit the servers, their amount of power goes up, their heat dissipation goes up. This is really a transient situation. But to model it as transient would take so much time and data that it wouldn't be feasible. So we model it as a steady state, and we use these models to help guide the decision process associated with making good engineering decisions. It is not a substitute for good engineering analysis. It's a tool like a hammer, and you need to be able to use it appropriately and effectively to communicate whatever it is you're trying to communicate to the people that you're serving, whether it's a customer or whether it's your boss or whether it's the data center that you work for. CFD allows you to not only encourage good decisions, but it's an excellent tool for discouraging bad decisions. We find that it's as good as discouraging bad as it is as encouraging good. A lot of people will have bad ideas, not a lot. Some people will have bad ideas. And we use this as a way to illustrate that their idea may not be as good as they think it is. So with that, I'll sign off for today. I want to thank you all for coming. And I appreciate your time today. If you have other topics you'd like me to cover, send me a note. If you'd like a copy of this presentation, send me a note. My email address is paul.bemis@coolsimsoftware.com. Did I put it at the end? I hope so. Yes. So paul.bemis@coolsimsoftware.com. Would be willing to work with you on any of these, show you how it works, give you our advice. We've been doing this now for many years, have probably more collective experience in this organization than anybody out there. So thank you for your time today, and let me know if there's other topics you would like me to cover. Thanks. Have a good day.